All right, welcome back. We are going to move into module number 2 in the course here. In this module, we're going to be talking about secure extensible network deployment. Specifically, we have basically 5 different lessons that we want to go through. Number 1, we're going to talk about how do we secure control plane and the control plane operations. Number 2, how do we deploy a vEdge device and verify vEdge device operations. And then number 3, we're going to describe how to secure the data plane operations and how that data plane operates. We're also going to talk about identifying the different service provider, the different services, provided by the different cloud deployment options. And then finally, we'll wrap up this module by looking at the high availability redundancy options in this architecture as well. So let's start by talking about the secure control plane operation. Now this is a pretty extensive section here because we're actually going to be talking about the protocols themselves, the port numbers that we use to communicate, and really all the specific details about how the secure control plane operation works. So what is the zero trust model? What is the operation of the secured channel between the control elements? We're going to describe the operation of the secure control channel between the different vEdge routers, and then how the secure control plane is protected from things like denial of service attacks and so on. All right, so the first thing we talk about is this zero trust model and how this zero trust model works. So I'm going to kind of summarize first what they have in the book about this, and then we're going to get into, I'm going to give you guys a little bit more detail in, from my perspective and my experience about this zero trust model. But, obviously we've already seen throughout the discussion, there's a security element that's part of this that's kind of incorporated in every aspect of the deployment, right? We have authentication, we have DTLS tunnels and TLS tunnels that are created, which means there's some RSA certificate-based authentication that takes place as well. And the vSmart controller is what does this particular authentication to all of the different vEdge routers before we can actually even send any traffic over the network. All right, we know that the vEdge devices or any of the endpoint devices, or when they join the overlay network, they automatically validate themselves, they automatically authenticate themselves to establish that secure communication channel, right? And the vBond orchestration is the piece that actually handles most of that. And that's that daemon, that software application that runs on the vEdge devices, that allows that process to take place between the vSmart controllers and the vEdge devices. Obviously, as an administrator, you're going to have to configure this and set this up, and you're going to download all of the authentication related files from the vManage NMS, and then the devices will automatically receive their configurations from vManage through their relationship with the vSmart controller. All right, there's a certificate signing request that has to take place. The NMS and in turn the vSmart controller acts as a certificate authority in some sense by sending out this certificate information. We install the received certificate, and there's some commands that I'm going to talk about in this section here that allows us to verify whether that process has taken place correctly. And then based on the serial numbers of the endpoints, which are included in the certificate, the vEdge routers then will go through the process of registering to the vSmart controller and then uploading or downloading their configuration based on that authentication. And that's when we talked about this whole zero-touch provisioning process that I'm going to go into details on as well. So this automatic process is all handled and all managed by the vBond orchestrator. And under that vBond software direction, where the device gets set up, the encrypted communication channel gets set up, and then over those channels, we automatically validate and authenticate the devices and so on. So I want to go into a little bit more into this because I think it's important to understand, but that's kind of just a summary of what they're talking about on this particular slide. Obviously, SD-WAN, when we look at it from the perspective of just a regular WAN, the SD-WAN piece obviously incorporates a lot more security than just your traditional WAN. Not that you can't run IPsec or some other sort of tunneling and encryption method over a traditional WAN, but it certainly doesn't happen automatically. So with the zero trust model, the security approach is in SD-WAN, right? The thrust of this zero trust security approach is to stop trusting applications, stop trusting the users, the networking devices, or even the networks by default, and instead implement kind of a regime, if you will, of continuous verification. In other words, this zero trust model focuses on authenticating first and then providing network security access secondarily. And that's what they're pretty much describing on the slide here, right? We enhance the performance and if you will, I guess, the agility of the WAN by introducing software-defined technology that can work with the current infrastructure that we have in place. And it should follow this zero trust model. You think of zero trust, the term zero trust literally means we're not trusting anything, right? And that's where we get the end-to-end circuit encryption from on-premise to the cloud by using this IPsec 256-bit protection. It's the idea is that we're trying to help IT managers better control and monitor who's accessing the network, which applications are accessing the network, and we do this by, in essence, strengthening all of our access control policies. And so we have to have software-defined, if you will, stateful firewalls to our edge devices. So this whole architecture, even though it's completely integrated, does require a whole new security approach. Transactions move to the cloud, and the internet and networks are, in this case, particularly in this case, are going to be highly distributed. So we have a whole bunch of different attack surfaces, if you will, or different attack vectors that we have to be concerned with. Our applications, our users, the devices themselves, the data itself has moved outside of the traditional zone, if you will, of control. And we've always kind of had a standard definition of what protected zones were based on, a very, very specific design in the enterprise. What is the enterprise core and what is the enterprise edge? And we had a very easy way of distinguishing what would be trusted and what's not trusted based on that. So building and enforcing a security model that relies on a corporate perimeter in the case of a WAN is really not possible in this case. And that's why we talk about this zero trust security model, all right? So the zero trust security model assumes that there's really no inside. It basically also assumes that every user and device is equally untrusted. Every access request is going to require some sort of authentication, some sort of authorization. Applications and data are only going to be delivered after verification takes place, and then on kind of a transient basis, if you will, with limited scope, right? Where that's the authorization component, that limited scope. It treats basically all applications as if they're internet facing, and it considers the network to be compromised and hostile. And these are things that you'll see if you go out and read documentation on the zero trust model. These are kind of the common terms that you see that describe this whole concept of zero trust. There are some core tenets of the zero trust model, just generic core tenets that are typically defined, right? Make sure that all resources are accessed securely, no matter where you're located, right? Regardless of the location, or even regardless of the hosting model. We have a least privilege and default deny strategy when we're enforcing things like application access. We always inspect and log the traffic, not only for applications that we control, but also even the applications that we don't control. And our goal there is to identify malicious activity. So there's two major components that support the implementation of this zero trust security. The first is you have to have some sort of identity-aware proxy for secure application access. And this is all incorporated in the implementation of the SD-WAN, but these are the tenets that govern that implementation, right? We also have to have a secure internet gateway for protecting users. And we're going to break down actually these proxy components and the gateway components in this section here when we get into some more detail. All right. I guess the thing is to say that the key component of any IAP is an identity source that verifies the user and somehow does some sort of device trust. And both verifying the user and doing the device trust is a form of authentication. And then on top of that, what do we allow them to do? What resources do we allow them to access? And that's the authorization piece. So it's always going to be about authentication and authorization. The identity source may be based on corporate directories. It could be cloud-based identity providers. It could be internal policies or procedures that you implement. But even before the user's identity is going to be validated, we need to check the device's posture to ensure that the device that's attempting to gain access meets the certain security criteria. Do they have the right certificate? Are they running the latest operating system? Is there some sort of secondary authentication, like are they password protected? Do they have the appropriate endpoint detection and response solution installed and operational on the device itself? These are the tenets of any kind of zero trust security model. We see this actually quite a bit when we look at implementing network access control with the identity services engine, right? These are the same kind of concepts that we discuss. All right. So one benefit of this IAP model compared to maybe more traditional kind of static security models is that not only are users verified, but the user's traffic gets inspected. Individual application requests can be terminated if they need to be. They can be examined. They can be authorized. Once a transaction is terminated on a proxy, we can actually integrate additional services as well. And I don't know that we're going to get into the specifics of that in this part of the class or not, but I just want to make sure that you understand what the entire concept of the zero trust model represents when we're talking about the bringing up this virtual fabric, right? We have application level access controls. We don't have firewall rules, so it's not like a static security policy. We have these configured policies, these dynamic policies that reflect users and applications' intent, not just, hey, what is the port that they're using, what are the IP addresses they're coming from, and so on. The critical aspect of transitioning to any kind of zero trust security model is to make sure that users remain safe while they're accessing the applications that you don't control. And that's kind of what we're assuming in this case. We're not just identifying applications that we see on a regular basis or that we know that are going to exist. Because a lot of the cyber threats that sit behind the scenes, or a lot of the cyber threats that exist, are based on those applications that we don't necessarily control. All right. So we're trying to protect against things like malware and ransomware, phishing attacks. But I mean, you traditionally would do that, right? In the past, we would always implement some sort of antivirus application or endpoint protection. And then we'd have a stack of appliances in the data center, and we'd backhaul the traffic, and we would do our traditional inspection and control. That doesn't really scale well to a SD-WAN environment. So a simpler, a faster, kind of a more cost-effective method of securing the DIA traffic is to basically use some sort of cloud-based security internet gateway, and that becomes our kind of safe on-ramp to the internet. And that's what they mean by the fabric bring up in this particular case. It provides us that option. So that's in essence what the zero trust security model is. They're going to go into a couple more concepts here on the next couple of slides, but and we'll break it down here. But that's kind of what I wanted to mention in addition to what the book had about the zero trust concept. So what we're seeing on this particular slide here is kind of how these virtual firewalls get deployed, right? You've got your vBond orchestrator in the middle. That's sitting in the DMZ. And then you got your vEdge router and your vSmart controller that have some sort of firewall concept, or at least some sort of security concept. The automatic validation and authentication of the SD-WAN devices during the bring-up process. Remember, the orchestrator is only part of that bring-up process. And we talk about the bring-up process being essentially when the vEdge devices are registering and communicating with the vSmart controllers so that they can join the fabric, if you will. All right, that bring-up process only occurs if the vSmart controllers and the vBond orchestrator know the serial number and the chassis number of the devices that are permitted into the network. And that's where the zero trust provisioning piece comes into play, which we're going to get into a little bit later on. So what is the serial number? Every SD-WAN device has a serial number. It's a 40-byte number that's included in the device's certificate. And then the vBond orchestrator and the vSmart controller, that certificate is provided by a Symantec or some sort of enterprise root CA. And then for the vEdge routers, the certificate is provided by the hardware's trusted board ID chip that's built into the router itself. That's that trusted platform module that we were talking about previously. We were talking about the vEdge devices. The chassis numbers were pretty simple. It's just a router is identified by a chassis number. There's a one-to-one mapping between the serial number and the chassis number. So these are unique values to each of the devices. And then the vSmart controller and the vBond orchestrator will actually learn about the serial number and chassis number during the initial configuration of that device. And in one of the previous lessons we talked, I kind of walked through the step of how a vEdge device is provisioned. We're going to go through that again, but in more detail the next time and talk about that. But there are authorized serial numbers and then on the vSmart controller, and then there are authorized serial number files on the vEdge devices. The vSmart authorized serial numbers, which is actually facilitated through vManage, right? vManage actually learns those serial numbers for all the controllers that are allowed to be in the network while it's creating a certificate signing request, right? And installing those signed certificates. And that's how we kind of capture all that information during that process. We download those serial numbers to the orchestrator, and then the orchestrator pushes them to the controller during the automatic authentication process. The nice thing about this, and hopefully in the next exercise you'll have an opportunity to deploy a couple of endpoints, but the nice thing about this is pretty much a completely automated process. It's not something that you have to manually facilitate, right? It's built into the software that's being deployed in the SD-WAN architecture, all right? The vEdge authorized serial number file that contains the serial number and the chassis number of the vEdge routers. These would be registered as well, and that's what allows those vEdge devices to be part of the network. We have to upload those files to the orchestrator and the vSmart controllers, and we can use templates to do that. And we'll talk more about templates probably tomorrow. I don't know that we'll get to the template stuff today, but Probably tomorrow we'll talk more about the template deployment and how we register devices to the vSmart controller through vManage. In addition to the device's serial numbers and chassis numbers, this automatic validation and authentication depends on having each device configured with the same configuration organization name. We configure that through the NMS, through the vManage NMS, and then that's included in the configuration file that's on all the devices as well. All right? Just a component that has to be configured as part of the process. Okay? All right. So this section here, this particular slide here describes, they kind of break it down to a pretty basic concept. But I'm going to spend a little bit more time on this because I think this is a really, really important concept. The communication that occurs between the different endpoints, the vManage, the vBond orchestrator, and the vSmart controller. We'll start by kind of just talking about what they're mentioning here in the slide, and then I'll get into kind of more specifics that I think are important, right? So if we're looking at the diagram here, it says certificates are exchanged for mutual authentication, meaning that both parties authenticate each other. We're not just doing a single party authentication. If you're familiar with the way RSA works, we have digitally signed certificates, private and public certificate keys, and we present our public certificate, which is digitally signed by a third party that is trusted by every party, right? And as long as that certificate is signed, we're able to authenticate that endpoint because they were already previously authenticated by a third party. In this case, it would be the CA that we've established as our root CA for the entire domain, right? vBond validates the vSmart controllers and vManage certificate serial numbers against an authorized allowed list, which you configure as an administrator. The vSmart controller and vManage validate the vBond orchestrator certificate organization name against a locally configured one, which you configure. And then we have DTLS and TLS to establish the secure connection so that we can make sure that this stuff is exchanged over a private line, not over public domain, right? That's the whole purpose of having the DTLS piece in place. All right, so it says here as a sample configuration, we have a controller group list 1020, which identifies the organization name, Viptela Inc., regression. That's just a name that you decide for the organization. It's just an example in this case, and then the time zone. All right, so it says here to initiate a session between a vSmart controller and the vBond orchestrator, the vSmart controller initiates an encrypted DTLS connection to the orchestrator. And remember, the orchestrator is just software that's running on these, either the platforms like the vSmart controller, which is just a software platform, or it's a daemon that runs on the vEdge devices as part of the software on the vEdge device. The encryption is provided by RSA, Rivas, Shamir, and Edelman. It's just a public key infrastructure cryptography process. Each device automatically generates an RSA private key and public key pair when it boots up. These are self-generated private and public keys, and they're not at this point digitally signed, but they have been generated, all right, based on the device's local information. Over the encrypted channel, over that DTLS session, the vSmart controller and the vBond orchestrator authenticate each other. After that bidirectional authentication is completed between the two devices, the DTLS connection between the orchestrator and the vSmart controller transitions from being a temporary connection, because we hadn't actually technically gone through the process of authentication, to being a permanent connection, and then that's when the two devices establish an OMP session over that particular connection. All right, So the vBond orchestrator has only as many permanent DTLS connections as the number of vSmart controllers in the network topology. Meaning that if I have 3 vSmart controllers, I'm going to have 3 DTLS sessions in that particular case. No data traffic flows between them. The controllers basically just register themselves, and then the orchestrator and the vSmart controllers are ready to validate the vEdge devices that are going to be attached to the network. All right, so that's kind of how the book described the process. But there's a lot more to this process than just that, and that's why I want to take some time to kind of go through this and break it down a little bit more, because there's a bunch of port numbers that need to be identified, and there's a communication process that needs to be identified, because you're going to have to allow this communication through your transport, right? The secure sessions that happen between the vEdge routers and the controllers, and between the controllers themselves, is DTLS. Now DTLS is UDP based, right? So one of the things that you need to know is what is that default UDP port number that's going to be used for that temporary DTLS session. And that's 12346, I believe. Yeah, 12,346 is that default base source port number. We'll actually see later on in the book, they'll discuss these ports again later on. I want to mention them right now because I think it's important. It's part of this discussion. All right. Now, there is another concept in this registration process. It's called port hopping, where the vEdge devices will actually try different source ports when they're trying to establish connections to each other in case the first connection through the first port fails. So basically what's going to happen is that the vEdge device is going to increment that port by 20. It's going to try 12,366, and then it's going to try 12,386, and then 12,000, what did that be? That'd be 406, and so on, right? 12,426, and so on. And then eventually it'll return back to 12,346. Obviously, hopefully at some point we're able to identify one of those open ports and be able to establish the session using that hopping method. All right. Now, port hopping is configured by default. I've seen it actually in operation from time to time. Usually the standard base port will work, but I have seen it where it hops from up to maybe the third iteration of that. But it's enabled by default on the vEdge routers. You can disable it. You can disable it either globally in the whole system or on a per tunnel interface basis. But it is recommended generally, I think it's even documented in the best practices design guide to run port hopping at the branches, but disable it in the specific controllers themselves, right? Disable it at the data center if you have a regional hub, if like it's a hub and spoke environment, or anywhere that you have some sort of aggregate traffic, you should disable the port hopping. But for the branch locations, it's just fine. Control connections on vManage, if we have multiple virtual CPUs, are going to have different base ports for each virtual CPU core. So that's going to change on the vManage side. For vEdge routers that sit behind the same NAT device, if they all share a public IP address, we do not want each vEdge to attempt to connect to the same controller using the same public IP and port number. And that's why we have this offset to the base port numbers, so that port attempts are unique, right, for each of the vEdge routers. So that's kind of the scenario that I was describing before that I saw that situation occur. Was because we had similar IPs trying to use the same port number. All right. Now, the port offset in this case doesn't necessarily have to be the hopping offset. It could be a port offset of 1, which means that the vEdge might use a base port of 12,347, and then it might port hop based on increments of 20 from that. So it could be 12,367, 387, and so on. You actually have to configure as an administrator that port offset. So you need to identify the vEdge devices that might fall under this scenario where they would come from the same IP address because they're behind the same NAT device. But then you would configure that offset explicitly. And by default, there is no offset, right? The default port offset is actually 0. So we can use that, or we could use a TLS to connect to vManage and vSmart. That is going to be TCP based instead of UDP based. The DTLS is UDP based and the TLS is TCP based. And then the TCP ports that originate on the vEdge devices are basically random port numbers, and they're going to send the traffic to a standard base port of 23,456. The control connections, if I have multiple CPUs, will have different base port numbers for each core, each vCPU core, very similar to what we saw with DTLS. Now, on top of that, if you remember, we're also running Ipsec tunnels and BFD from the vEdge router to other vEdge routers. That's going to use UDP with similar ports that we defined for the DTLS process. So the firewalls in the network need to allow communication between the vEdge routers and the controllers. Make sure that those firewalls, and that's why we're talking about this in more detail, are configured to allow return traffic, not only just the outbound traffic. All right, we'll see this again. There's like I said, a slide in the book itself that kind of goes through this process and talks about these port numbers. I'm familiar with the process because I've seen issues where communication fails based on that. And I think it's important to know those port numbers. And there's documentation on Cisco's website that describes that whole process. All right, and describes all the port numbers that are required for that communication process. All right. So how do we do the authentication between vSmart and vBond? All right. The communication process is it's kind of basic. You know, you look at the diagram here. It says, "Authenticate me." Okay, you are valid. Authenticate me. You are valid. All right. So that's pretty obviously a generic way of looking at this, right? And then we establish the DTLS tunnel. When a vSmart controller comes up, the first thing it does is it initiates a connection to the vBond orchestrator. And that's how the vBond orchestrator then learns about the controller itself. Remember, the vEdge devices are basically going to do the same thing. The vEdge device and the vSmart controller are the ones that ultimately need to talk to each other. But if you recall from our previous discussion, the orchestrator, the vBond orchestrator, is the one that facilitates that communication. It's the piece that facilitates the authentication and the authorization of those particular relationships. Once that occurs, once the authentication occurs and the authorization occurs, the vBond orchestrator kind of steps out of the picture, if you will. All right? But there is a two-way authentication process. The controller authenticates itself with the orchestrator, and then the orchestrator authenticates itself with the controller. There's a handshake between the two devices, and that occurs in parallel. It's not that it happens in one direction, then it happens in the other direction. It's kind of happening in sync, right, in parallel. All right. This is a high-level representation, obviously, this particular diagram. It's a much more involved process. So, again, this is kind of a long discussion, even though there is not a lot of detail on this slide. I think it's important to understand the specifics of this process as well. And so I'm going to kind of get off on a little bit of a tangent here and describe all of the different aspects of this communication. So it's really important, right? The control plane of any network is really concerned with determining the network's topology and defining how we direct traffic. That's the basic concept of any control plane function. In a traditional network, the control plane operations of, say, building and maintaining routing and forwarding tables and directing packets towards their destination, that's going to be handled by your routing protocols and your switching protocols, which typically offer really no mechanism for authenticating devices and certainly no mechanism for encrypting things like routing updates and other control information, not by default. Authentication can be built into these processes. We have hash-based authentication mechanisms like with EIGRP and OSPF and so on, even some other control plane protocols, but from an encryption standpoint, there's very, very little that's available. Additionally, whatever traditional methods that we have for providing security are very, very manual, right? You have to configure them statically, and they just don't scale very well in an automated network design, right? Or even as the network grows in size. Certificates are typically installed manually, or we're using some sort of pre-shared key, which is not really a very secure approach to providing device security. Now, flip that over, and if we look at the viptela control plane, it's been designed, and that's what we've been talking about for the past 35 minutes or so, is designed to work with security in mind, right? That zero trust model that we talked about means that everything has to be authenticated and secured before we allow anything to happen. So the foundation of the control plane is really one of two different security protocols that were derived from SSL. And we've already mentioned them a couple of times, right? DTLS, the Datagram Transport Layer Security Service or protocol, and TLS, the Transport Layer Security Protocol. The vSmart controller, which is the centralized brain of the entire viptela solution, is going to establish and maintain either a DTLS or a TLS connection to every other viptela device in the overlay network. That would mean the vEdge routers. That would mean the vBond orchestrator, and that would mean the vManage NMS or any other vSmart controller, right? I mean, there's four major pieces, right? We talked about this multiple times: vEdge devices, vSmart controller, vBond orchestrator, and the vManage NMS. All right. Any of that traffic that the vSmart controller is creating over that DTLS or TLS tunnel is going to carry our control plane traffic. So the DTLS piece or the TLS piece is what provides communication privacy between the different viptela devices on the network, and it's going to be based on AES 256. And we're encrypting for confidentiality, encrypting all that control traffic that's sent over those different connections. Does that make sense so far? Okay. So the privacy and encryption in the control plane that we get from DTLS or TLS provides that secure foundation for the other two security components, which are authentication and integrity. All right, to perform authentication, we use those digital certificates that we talked about. The certificates, like I said, are either installed by the software or they're hard-coded into the hardware, depending on what type of device we're talking about in the environment. But they're used to identify the device and then to allow the devices themselves to automatically determine which ones belong to the network and which ones are not supposed to be there, which ones are imposters, if you will. Okay? So for integrity, we use SHA-1 or SHA-2, which is basically just a cryptographic secure hashing algorithm, which ensures that all of the control and data traffic that's being sent over the connections hasn't been modified or tampered with. So we've got confidentiality, which is provided through AES encryption, and we've got message integrity, which is provided through SHA-1 or SHA-2. All right. So we've got three major pieces that I just mentioned. AES 256 for encryption, digital certificates for authentication, and then SHA-1 or SHA-2 for message integrity. Those are the kind of the cornerstones of the security architecture. Typically the three things we talk about. All right. Now, DTLS as a protocol itself is a transport privacy protocol. And that's typically used for connectionless datagram protocols like UDP. And that's part of the foundation of the control plane infrastructure, if you will. All right. It's loosely based, well, maybe not even loosely based. It's probably more strictly based on TLS, which is a security mechanism provided for TCP-based application. And TLS, of course, evolved from SSL. So why do we have both, right? Why do I talk about DTLS and TLS? Well, in the viptela infrastructure, it's actually designed to use DTLS over UDP to avoid some of the issues with TCP, like delays that are associated with any kind of streaming protocol, and maybe even some security issues that might exist with those protocols as well. But because UDP doesn't really perform any handshaking, it doesn't send acknowledgments, DTLS has to handle packet reordering. There has to be a way for us to handle maybe the loss of datagrams. And if we have data, say, larger than the datagram packet size, we might have to segment that information as well. All right, so the control plane infrastructure can also be, even though it's not by default, it can also be configured to run over TLS. And that's where you might say, okay, I'm going to choose to use TLS in this particular case because the protections of TCP that I get, especially when it has to do with things like reordering of data or loss of datagrams and segmentation, is going to outweigh whatever issues are introduced with utilizing the TLS piece. All right. Firewalls, for example, are much better at protecting TCP than UDP. Okay. Now, viptela software implements standard versions of DTLS with UDP. That's based on, gosh, now I have to remember, RFC 6340. I might have to look this up. I think it's 6347. Don't quote me on that, but I think it's 6347. And then we also identify some other RFCs, but I think that's the primary one. And then for TLS, it's RFC 5246. That one I happen to know because I was looking up that RFC not too long ago for a customer. All right. So by default, in our viptela architecture, we're going to use DTLS or TLS as a tunneling protocol. It's a layer 4 tunneling protocol, by the way, because it does ride on top of UDP or TCP. All right. And as we described, and that's what this slide is kind of indicating here, when the vSmart controllers, when the vBond orchestrators, when the vManage NMSs, when the vEdge routers join the network, they're always going to create that provisional DTLS or TLS tunnel between them as part of the authentication process. Once that authentication process successfully completes, the provisional tunnels that exist between the vEdge routers and the vSmart controllers and the ones between the vOrchestrators and the vSmart controllers become permanent, and they actually stay up. They stay up as long as the devices are active in the network. So you're going to have these tunnels, and I think you kind of asked about that previously. You know, from a scalability standpoint, is this going to be a lot of extra load on the network? And again, it's not really that significant. It's kind of like in a controller environment, like a voice over IP environment, you know, having a SCCP signaling process or having a a SIP control process is going to be kind of relatively benign compared to the actual transport of the data itself, the media, or in the case of the viptela architecture, the data between the vEdge devices. Okay? All right. The devices that get authenticated, it's those devices, the secure DTLS and TLS tunnels that are used really by all protocol applications running on a viptela device to transport the traffic. So every aspect of communication is now secured. And that's where that zero trust model comes into play. We're saying, look, we don't trust any endpoint. We're going to authenticate and authorize every single endpoint. And then not only that, we're going to encrypt the traffic that is passed between those endpoints. So let's say, for example, we have an OMP session, right, on a vEdge router that communicates with an OMP session on a vSmart controller. And we're sending plain IP traffic through that DTLS or TLS tunnel between the devices. If you remember that OMP traffic, the Overlay Management Protocol, that is the control protocol used to exchange things like routing information, policy configuration information, and other management information between the devices themselves. We actually have a daemon running on each vSmart controller and each vEdge router that creates and maintains those secure DTLS tunnels and TLS connections. And that daemon is actually called the vDaemon. Everything starts with a V in this architecture. So the vDaemon is what allows this communication, right? It's after the control plane, specifically the DTLS or TLS connections are established, lots of protocols can create sessions to run and route traffic over those particular connections. You might have, for example, OMP. We talked about that. You would have that typically anyway. You might have SNMP as well. You might have NetCom for a network configuration protocol. But we don't really need to concern ourselves with the security of that information, right? Because it is going to automatically be secured by those tunnels, right? That session-related traffic is directed over the secure connection between the vEdge routers and the vSmart controllers. All right. We talked about the authentication piece as well. What I was just mentioning there was really just the whole infrastructure, the DTLS, TLS infrastructure. But we also have our control plane authentication. And it happens between multiple devices, but that's what this slide is basically referencing, right? We use digital certificates. Those are going to be 2048-bit RSA keys. And they're created and managed and exchanged by using the public key infrastructure, right? We have public keys, which are generally known to everybody in the architecture. We have our private keys. They reside on each of the individual devices, and they can't be retrieved, and they're never shared with anybody in the network. And then we have the certificates, which are signed by the root CA, and then there's a trust chain that gets created with the root CA that has to be represented on all of the devices. And that's a standard PKI concept, right? The certificate root or the CA root certificate needs to be installed to create that trust chain between the different devices. There are some other components, right? We talked about that in the last slide, actually. Each viptela device has a serial number, and the vEdge router chassis numbers are also used during that authentication process. All right. So let me actually go back one slide because that's what we're talking about in this piece here. Let me actually see if, yeah, it's kind of related to this piece as well, but we'll get into that slide in a minute here. All right. So on the vEdge routers, you have your public and private keys and the certificates, which get managed automatically. There's a trusted board ID chip that's built into the router itself. And when the routers get manufactured, that chip actually gets programmed with a signed certificate, which includes the device's public key and its serial number, and also includes the device's private key. So when a vEdge router boots up and it joins the network, they're going to exchange their certificate, including the public key and the serial number, with any other Viptela device as part of the authentication process. Now, if I have thousands or tens of thousands of vEdge routers, this obviously makes my life so much simpler, right? Because I don't have to manage certificates and installing certificates on these devices as part of the process, right? It's just part of the manufacturing process. So it really reduces and simplifies the task of maintaining security with the devices. Now, vEdge router private keys always kind of remain embedded in that trust board ID chip because they're private. They never get distributed, and you can't actually retrieve them. But you know, somebody may attempt to do so, right? Somebody may attempt to try to read that private key so that they can break that certificate trust. If that happens, basically access to the device is completely disabled. The device is actually programmed to recognize that. It's going to cause that trusted board ID chip to fail, and then it's going to disable access to that device. So it's kind of a fail-safe mechanism. You're still protected against denial of service, though, with other mechanisms. We don't have to get into the details there. All right. Now, for the vSmart controllers, for the vBond orchestrator, for the vManage, the public and private keys and the certificates are managed manually, but we don't have that many of those devices in our topology. So when we boot those devices for the first time, the device itself is going to generate a private key and a public key pair for each software image, but then that public key needs to be signed by the CA root. So you're going to, as a network administrator, request a signed certificate, and then you're going to manually install it and whatever other certificate chains are necessary on the controllers, the orchestrators, and the vManage systems. So that part is, when you're setting this whole system up for the first time, that's a part that takes a little bit of effort, a little bit of time. All right, but typically, again, in most SD-WAN implementations, you're only going to have a handful of vSmart controllers and vBond orchestrators and maybe even one or two vManage NMSs. So manually managing those keys and certificates on those devices, that burden is kind of small in this case. It's really the vEdge devices that would take a long time. All right. So like I said, to augment the public key infrastructure components, the Viptela software uses things like device serial numbers when we're doing the automatic device authentication. Specifically, it uses the vEdge and the vSmart serial numbers, the vEdge chassis numbers, and then when we batch, if we have a batch of vEdge routers that get shipped out, the manufacturer actually will send you a text file that lists all of the serial numbers of those vEdge routers and chassis numbers. So you can actually import that information through the use of a template, which we'll talk about later on, without having to capture that information yourself. For the vSmart controllers, when you receive a signed certificate, you need to extract the serial number from the certificate and then put those serial numbers into a single text file. There's a specific format for that file, and you can download that as a template as well. And then you would have each one of those serial numbers listed in an individual line. Then you manually install those two files, the one that came with the vEdge routers and then the one that you created for the vSmart controllers. And then that allows us to identify all the valid vEdge serial numbers and chassis numbers and the vSmart controllers. Both the vEdge authorized serial number files and the file listing that you created listing all the vSmart serial numbers get uploaded. But where do you think they get uploaded to? What's the one device in this entire architecture that is supposed to facilitate this registration process? Do you remember? The vBond orchestrator, right? So that's where we're loading that information to each of the vBond orchestrators. So during the automatic authentication process, as pairs of devices start establishing those DTLS control connections between them, each device compares the serial numbers and if, again, with the vEdge routers, it's not just the serial number, it's also the chassis number, to those files that are installed on the device. A device then allows the connection to be established only if the serial number or the chassis number combination matches whatever is in that list or in that information that you installed. Okay? So there's a couple of commands that you can use to display this. If you want to look at all the vSmart authorized serial numbers, you can use the show control valid vSmarts command. We'll see that a little bit later in the book as well. You can use the show orchestrator valid vSmarts as well on the vBond orchestrator. The show control valid vSmarts command, that would be done on either a vEdge router or a vSmart controller. The show orchestrator valid vSmarts command would be obviously done on the vBond orchestrator. All right. If we want to see the vEdge authorized serial and chassis numbers, we would use the show control valid vEdges command on the vSort controller. And on the orchestrator, we would use the show orchestrator valid devices command. Again, we'll see, hopefully you'll see those commands a little bit later on when we get more into the configuration. All right. So it's a lot of information. I told you this was going to be a pretty lengthy discussion. Somehow I switched over the slide there. We're not quite on this slide yet. We've got a little bit more to talk about. Because remember, I've only talked about the authentication piece, the control plane authentication. I haven't even talked about the control plane encryption and the control plane integrity, which I'm still going to talk about in details here. All right. So let's talk about that. Let's talk about the control plane encryption, and then I'll talk about the control plane integrity. We've done all the heavy lifting. The encryption is kind of pretty straightforward, and the integrity is pretty straightforward. The encryption itself is either done by DTLS or TLS. We talked about the reasons for choosing one or the other. And both of these protocols encrypt that control plane traffic that's sent across the connections between the different Viptela devices to validate the integrity of the data. So we say encryption and then we talk about integrity. Well, yeah, encryption does provide some sense of integrity because it's providing that confidentiality. We do have a separate integrity mechanism, but obviously encryption is going to help with that process. Okay. TLS uses asymmetric cryptography for authenticating key exchange, and then symmetric encryption for confidentiality. That's pretty typical, right? Asymmetric for key exchange, even if it's like a traditional IPsec, we're going to use something like Diffie-Hellman for key exchange, which is an asymmetric key exchange process. And then we're going to use some sort of bulk encryption mechanism, which is typically symmetric. Keep in mind that each of these devices, whatever it might be, can have multiple DTLS or TLS connections to other devices as well. So that vDaemon that we talked about creates what we call a kernel route for each destination. Let's say, for example, a vEdge router typically has one kernel route, and hence it's only going to have basically one DTLS or TLS connection for each vSmart controller that it's connected to. But a vSmart controller could have one kernel route and one DTLS or TLS session for each vEdge router in its domain. But obviously we can have more than one vEdge router attached to a vSmart controller. So you might have multiple tunnels, okay? Most likely you would. The integrity, as I mentioned before, SHA-1 or SHA-2, message digests to provide the integrity. These are cryptographic hash functions. They generate message digests or just digests. A lot of people just simply call it a digest for each packet that gets sent over that control plane connection. SHA-1, still relatively secure. It generates a 160-bit message digest. SHA-2 has a whole family consisting of 6 different hashing functions. So 224, 256, 384, and 512. And the receiver generates a digest for the packet. So if I'm sending you information, I'm going to send you the information. Encryption separate, right? That's done with the DTLS or TLS tunnels. But I'm going to send you the information along with a hash of that information and some secret sauce, which is usually some secret keying material. In this case, certificate-based keying material, the private key. And then you're going to verify it with the public key. But basically, you receive that digest with the packet. And if I can validate that digest by basically running the same hashing process, then I've verified that the contents haven't been tampered with. All right? So a part of this is the use of those public and private keys. When a control plane connection is being established, the local viptela device is going to send a challenge to the remote device. And then the remote device is going to end up encrypting. The remote device is going to end up encrypting, sorry about that. It's going to end up encrypting that communication channel when it's being established, right? So the remote device encrypts the challenge, it signs it with its private key, and then it returns that signed challenge to the local device, which is then verified with the corresponding public key to verify that you are who you say you are. This is all basic cryptographic functions, right? These are not unique to Cisco SD-WAN or unique to viptela. It's just we're making use of this public key infrastructure and this architecture to secure the environment. Finally, I guess, once that control plane is up, the keys are used to ensure that things like packets have been sent by a trusted host. They weren't somehow inserted midstream or somehow modified midstream by some untrusted evil Eve person in the middle. And then the authenticity of each packet gets verified through encryption and decryption using that symmetric key process that we talk about for the bulk encryption. Okay, so those are like the major pieces, right? The integrity piece, the encryption piece, the authentication piece, and thankfully you don't have to worry too much about this from a design perspective or from an implementation perspective, because quite frankly, it is essentially managed by the entire. It's managed by the software, right? This is all built in and kind of created and managed by the software itself, so you don't have to worry about it too much. All right. I don't know if that introduced more questions or it kind of helped answer some questions, but anyway, hopefully that helped at least alleviate some of the questions that you might have had about the process. All right, that's that whole zero trust model that we've been talking about, right? We're not going to trust anything, which means we're going to secure everything. All right. So let's go ahead and go through the process here. I'm kind of just going to walk through the process for each of these next few slides here, because they're really just kind of documented processes that you can read about. But each device authenticates each other in parallel. All right, so in this case, we're going to talk about what happens between the vSmart controller and the vBond orchestrator. All right, first thing that happens is the orchestrator sends its trusted root CA signed certificate to the controller. That would be its public certificate. The orchestrator sends the vEdge authorized serial number file to the controller. The vSmart controller then uses its chain of trust to extract the organization name from the certificate. It's going to compare that information to the organization name that's configured on the vSmart controller itself. And if those numbers or if those values match, then we know that the organization of the vBond orchestrator is accurate, it's correct. If they don't match, then we're just basically going to deny the connection and tear down the DTLS session. All right. I'm on step number 4 now, which is verify certificates signed by the root CA. So the vSmart controller in this case uses the root CA chain to verify that the certificate has been signed by the root CA. Could be your internal enterprise CA, or it could be semantic. If the signature has been verified, if the signature is actually correct, we know that the certificate is valid. If the signature is not correct, again, we're going to tear down that session. All right. So this is this is not really different than any other kind of authentication process. So, if you go to a web browser and you open up a connection to Bank of America or Citibank or something like that, well, guess what's going to happen? You're going to be presented with a digitally signed certificate from a digitally signed certificate from some sort of root CA. And either the web browser itself already has that certificate chain installed, or you have to go out and install it yourself. But we verify the identity of that or the signature of that certificate by looking at the installed and trusted certificates in the browser or on the computer. And that's what they're talking about in this case. The vBond orchestrator is saying, hey, here is my public certificate. It's signed by the trusted root. I'm going to go ahead, and by the way, here's the authorized serial number file as well. And the vSmart controller is going to verify the organization name in the certificate, which it should match, and then we can authenticate. In the other direction, it's basically exactly the same thing. The vSmart controller sends its trusted root certificate. The orchestrator uses its chain of trust to verify. We're also going to match the number of the vSmart authorized serial number file. If there's a match, we're going to go ahead and authorize it. If there's not a match, we're going to tear down the session. We're going to use our chain of trust to extract the organization name from the certificate, compare it to the organization name that's configured on the orchestrator, and if the two organization names match, then we know that the organization of the vSmart controller is accurate as well. So basically it's a mirrored process, right? And this happens in parallel. It doesn't happen, one doesn't authenticate the other first and vice versa. It just happens in parallel, all right? Even though it's always documented kind of as a unidirectional process, if you will. All right. Now we also have authentication between vSmart and vSmart as well. All right. And it's essentially the same thing. The only difference here is that we have serial numbers that we're identifying. But if I have multiple vSmart controllers, which you don't always have to have, but if I do have multiple vSmart controllers, then those vSmart controllers have to authenticate each other as well, so that we can have these DTLS sessions between them to synchronize OMP information and to provide that active-active failover in the event that maybe a vSmart controller drops off. We don't want to lose our control plane functionality if we lose a vSmart controller. So we have to have essentially live connections to each vSmart controller, and they have to be talking to each other as well. All right. So the vSmart controllers are going to learn about the IP addresses of other vSmart controllers from the orchestrator. Keep in mind, this orchestrator is the one that everybody registers to so that they can communicate with each other. And that's why it's called the orchestrator. It's the one that's orchestrating the buildup of this fabric, this entire SEN fabric. All right. So going through the steps again, 1, 2, 3, 4, 5, 6, 7, 8, 9. vSmart 1 on the left, in this case, initiates a DTLS session with vSmart 2. It sends its trusted root CA signed certificate to vSmart 2, which is a public certificate of vSmart 1. vSmart 2 uses its chain of trust to extract the serial number Again, the serial numbers have to match in the authorized serial number file that was installed manually by you as an administrator on the vSmart appliance. If there is no match, we tear down the session. If there is a match, then I'm going to go ahead and use my certificate, a chain of trust, to extract the organization name from the certificate. Again, I'm going to compare that to my locally configured organization name. And if those organization names match, we know that the connection is proper. If they don't match, we tear down the DTLS session. All right. vSmart 2 uses the root CA chain to verify the certificate, make sure it's signed appropriately by the root CA. Again, either a semantic CA or the enterprise CA that you have defined for your organization. And again, if the signature is valid, if I'm able to validate that signature, then I know that the certificate is valid and I can continue with the communication process. All right. vSmart 2 authentication of vSmart 1 is complete. So now we have our one-way DTLS session established. And now we do the exact same thing in the opposite direction. I'm not going to go through each of the bullet points here, but basically vSmart 2 now sends its trusted root CA signed certificate, and we go through the same process again. After both of these checks are done, after all 9 steps, I guess we say in this case, are done, then that temporary DTLS session that I was referring to before becomes a permanent DTLS session between the two controllers. Okay, you're kind of seeing a lot of repetition here, but that's kind of the point, right? I mean, this is all part of that public key infrastructure authentication and authorization. All right. Now, as I mentioned in my previous kind of long-winded discussion before about this trusted board ID chip, that's a crypto processor that contains the key information, right? That gets installed during the manufacturing process with the certificate itself. All of that information on that TPM is used for device authentication. They're managed automatically, right? It's built into the router when they're manufactured. We went through all that discussion already. And we have the serial number, we have the device's private key, the public key, and so on. So like I said, when the vEdge device boots up and it joins the network, it exchanges their certificates, including the public key and the serial number, with the other SD-WAN devices as part of that device authentication process. So we would have already had to have installed that text file that identifies our vEdge devices. Either we would manually create that text file, or the manufacturer, Cisco in this case, vendor, would create a file for you and send it to you if you're ordering a batch of vEdge devices. So if you order 10 or 15 or 20 vEdge devices, they're going to send you the file automatically. All right. And like I said, it's just going to greatly reduce the management of these devices. All right. All right. Let's see. So what we're looking at in this case is how do we authenticate those vEdge devices? We know it's a two-part process, right? We're going to be looking for the public certificate. The vEdge router is going to exchange its public certificate information with the vOrchestrator, and then vOrchestrator, or vBond orchestrator, excuse me, is going to exchange its certificate. So that allows us to create a connection to the vSmart controller, and then in turn the vManage platform, right? So we have to establish a secure connection with vManage. That's how we get our configuration. I talked about this boot up process in one of our very first lessons as part of this lecture, but that's how we receive our full configuration. And then the controller is what allows us to become part of the control plane functionality, right? So vManage is what pushes down the configuration to the vEdge device and the policy configurations to the vEdge device. And then the vSmart controller is what allows us to actually participate in the overlay network. All right. So it discovers, automatically discovers the vManage device, the vSmart controllers. We establish our connection with them as the vBond orchestrator kind of, it acts as an intermediary in this particular case. And then we get our configuration. We'll talk more about the zero-touch provisioning or manual provisioning process later on. I've kind of talked about that a little bit, but we'll spend some more time talking about that a little bit later on. All right, so the vEdge router is going to establish that DTLS session, and then they authenticate each other. Certificates get exchanged, and the vBond orchestrator validates the vEdge router and vice versa. We provision the temporary DTLS tunnels, and then those become permanent DTLS tunnels, once the authentication takes place. All right. That provisional DTLS tunnel gets established between the orchestrator and the edge device. That doesn't stay permanently, right? Once the orchestrator's done its job, it kind of gets out of the picture, and the communication is going to be directly from the vEdge device to the vEdge device, or for the data plane functionality, and from the vEdge device to the vSmart controller for the control plane functionality. All right. That's why they say at the kind of at the very end that provisional DTLS tunnel is terminated, because again, the vBond orchestrator is only there to facilitate that initial communication and registration process. Once that takes place, the orchestrator is not necessary in this case. All right. All right. Now, what if I'm communicating between vEdge and vBond? Over that DTLS channel, the vEdge router and the orchestrator authenticate each other. The vEdge router and the vBond orchestrator authenticate each other in parallel, just like we saw with the vSmart to vSmart and so on. And it's the same basic process, right? There's a little bit more information that gets exchanged, like the vEdge serial number, the vEdge chassis ID, the board ID certificate, and some sort of random value that's signed by the private key. That's kind of that challenge response type of thing that we talked about, where I send a challenge out and then you send a response so that I can verify that you have the appropriate public certificate based on the private certificate that I have installed. But outside of that, the process is pretty much the same, right? We're going to look at the organization name of the certificate. We're going to compare that to the organization name that's configured on the router. If they match, then we're able to authenticate the device based on that organization. Then we're going to verify the authenticity of the certificate by using that certificate chain, right? The root CA, to verify that the certificate has been signed by your enterprise CA or the semantic CA, and make sure that certificate is correct and so on. The challenge that gets sent is sent by the orchestrator, and it's a 256-bit random value. And then the response from the vEdge device is what includes all of that specific information from the vEdge device itself that only the vEdge device would really know, even though it's going to be manually configured on the vSmart controller and the orchestrator. The vEdge device has to present that information. That's like I said, that's the serial number, the random value that's signed by the router's private key, because only that vEdge router knows that private key. So it's kind of like, okay, here's this 256-bit value. Go ahead and encrypt it, right? That's what a digital signature is, right? It's basically a hash of the random value with the private key. Well, guess what? When the orchestrator receives that response from that challenge, it's able to verify the identity of the vEdge device, because it's able to identify the identity of the vEdge device because it's using the corresponding public key that was already presented to be able to verify that hash in essence. And because only the vEdge device would know what that private key is, then we're able to authenticate that device. We're also going to compare the serial number and the chassis numbers to that authorized device list that we installed. Those have to match in the file. We check whether the signing is done correctly on that 256-bit random value. And then we also use the root CA to verify that the router's board ID certificate is valid and the certificate itself is valid that's being presented by the vEdge device. All right. Now, vEdge and vManage, you know, it's kind of the same process, right? It's kind of the same process. We exchange certificates mutually. We verify those certificates by using the same process. We use the serial number and the chassis ID number on the vEdge device to verify the vEdge device with the vManage device. And then we use the certificates on the vEdge device, excuse me, the vSmart and vManage devices to verify those devices to the vEdge device. We always maintain a permanent DTLS tunnel and TLS tunnel between the vSmart devices, the vManage devices, and the vEdge devices. All right, that's always done. All right. Between vEdge and vManage, same process. I'm not going to go through this in detail here because it is literally the same process that we saw between vEdge and vBond, right? If you look, in fact, at these diagrams here, they're identical to each other. So it's literally the exact same process that we saw with the vBond orchestrator with regard to verifying those identities. So I'm not going to spend too much, actually any time going through this because that would be kind of repetitive. But it is the same process, okay? When we talk about vEdge and vSmart, pretty much the same. We still get the challenge from the vSmart controller. We still send a response that has the serial number of the chassis, that digitally signed 256-bit value, and so on. The only difference is the vSmart controller also identifies itself to vEdge. It's no different, actually. It's just kind of in the opposite direction. The vSmart controller challenges the vEdge device. So it's actually kind of literally the same graphic. The only difference is they're just depicting it in different directions in this particular case. All right. There is a permanent DTLS tunnel that becomes that gets established between the vSmart controller and the vEdge device, and this is where the OMP session resides, right? That overlay management protocol that we talked about. All right. This I mentioned as well, the default port offset, the base port for our UDP sessions, 12,346, and then the port hopping. I guess I don't really need to get into too much detail on this because I already kind of went through all this, but the idea is that we have to be able to identify the devices uniquely. All right, and typically you're going to see port offsets when you have, like I said, multiple vEdge devices that sit behind a single NAT device, which means they're going to look like a similar, they're going to have a same IP address because typically we're using some overload NAT or something like that, and that's where the offset comes into play. I also described the whole concept of port hopping, the default base port, and then the hopping sequence based on an addition of 20 to each port number. So 12,346 to 366 to 386 to 406 and so on. All right. Actually went through this entire thing previously. I should have just waited to this slide for that, but oh well. All right. This doesn't always have to take place, by the way. This port hopping option doesn't always have to take place. It's just a matter of where the vEdge devices are deployed and how they're establishing the connection to the SEN, right? All right. So the last thing we'll talk about before we wrap up this lesson is that the SD-WAN control plane obviously designed with security in mind, right? And one of the most common types of attacks that exist in any network, especially when you have automatic processes involved. Any kind of protocol that does automatic registration or automatic device communication is going to be susceptible to a denial of service attack because it's automatic. I mean, because of its automatic nature, if you will. So we're no different in this particular case, right? Now we have mechanisms in place to protect against distributed denial of service mechanisms. We have some control plane protection mechanisms that we have in place, and we'll talk more about the control plane protection piece a little bit later on. Actually, the next section is our secure control plane deployment section, so we'll talk about that. But the idea is that the vSmart controller, which is the central brain, if you will, of the whole SD-WAN solution, maintains these DTLS and TLS sessions between all of the devices in the overlay network. vEdge routers, the vBond orchestrator, the vManage NMS, and other vSmart controllers. I actually literally mentioned that in a previous section, right? Those are the devices, the vSmart controllers are the ones that carry all the control plane traffic. So by adding this encryption, adding the authentication, the mutual authentication, that's actually pretty critical. Adding that mutual authentication and the encryption, and on top of that, the integrity mechanisms really provides for that denial of service protection. There's some other things that we can do as well, for flows and CPU loads and packet forwarding to the CPU. So we can identify mechanisms for protecting the control plane. We see this in traditional routing architectures with control plane policing and control plane protection. We have those same functionality built into the SD-WAN architecture as well. And that'll be kind of one of the last things we talk about when we get into the last bit of our information that we talk about tomorrow. All right. So we might say, for example, let's go ahead and allow a certain amount of traffic to the CPU. And we use control plane policing, which uses MQC architectures to protect the control plane, where we have class maps to identify the traffic classes, and then we have policy maps to identify what we're limiting specific traffic to as far as rate limiting, and then we have our service policy, which is applied to the control plane interface, which allows us to do that rate limiting. So we do control plane policing on the orchestrator, we do it on the vEdge devices, and so on. We can say, for example, let's go ahead and deny anything to the CPU except for maybe DHCP traffic or ICMP traffic or netconf. And we can also enable things like stun or NTP, HTTPS. These would be protocols that are specific to vManage, but the idea is that we're protecting the control plane from being overloaded with superfluous information or information that's not necessary to manage the domain. All right. If you're familiar with the control plane policing concept, it's really no different here in this particular case. Right? We're limiting packets per second based on a flow, and some flows have more priority than other flows. The OMP is going to obviously have pretty high priority. But some other flows might have lower priority. All right, so even though that was a pretty lengthy section here, about an hour and a half, we talked about the zero-touch model. We didn't get specifically into the zero-touch configuration. We'll get into that a little bit later on when we get into the deployment section. But we talked about how devices authenticate and authorize themselves to join the SCN overlay network, how the controllers perform mutual authentication between themselves. The vSmart talks to other vSmarts. The vEdge devices are authenticated using different components, obviously the TPM components that are built into the device. DTLS is our secure channel. It's part of the overall control plane security, and no data traffic is transported over the secure control channels. We do have secure data channels that the traffic is passed over, but not the control channels. We talked about the mutual authentication piece between the controllers and all the different devices, and how the digitally signed certificates are transferred and identified. We talked about when we deploy our vEdge router in the network for the first time, it has to talk to the orchestrator, then it gets registered to vManage and the vSmart controller, so it can join the fabric and then also get its configuration. It discovers vManage and the controller through the orchestrator process, so that we have to have an initial configuration on the orchestrator that allows that vEdge device to be authenticated. And then we wrapped up this section by just talking about very briefly how distributed denial of service protection is provided in the overlay network inherently by doing all this authentication and creating these trusted resources. All right, so we'll wrap up this lesson, and we'll see you guys in the next lesson.